Hello everyone, welcome to this presentation where we're going to be talking about Altair's concrete design workflow. My name is Matt and I'll be leading the presentation today. And in this presentation, we're going to be discussing how we can go from basically a structural analysis model and the results associated with that model to a concrete design, which involves section design, the design of continuous beams, and also foundation design. Now, if you're not familiar with Altair, Altair is a global technology company. We actually have an AEC offering that comprises a number of different fields. So we'll be talking mostly about the code-based design available in S Concrete and S Foundation, but we offer a wide range of other applications ranging from blast simulation using explicit analysis solvers, CFD and thermal analysis, high-fidelity meshing, optimization for preliminary design concepts, and much more. And we're going to talk about how we can go from a structural analysis to a concrete design and really the workflow that accompanies that. So in this example here, we're looking at using S Concrete. And S Concrete, if you're just using the standard edition, or perhaps you've used it in the past, you're probably just working with one section at a time. It's got a very intuitive interface that allows you to generate detailed engineering reports while quickly and easily making changes to your design. However, it is not necessarily easy to use that standalone application when you have a large model that you need to draw in all the information for and create a large number of sections. And that's where this S Concrete Multi-Story Designer can really help out. And we're going to look at this example that you can see here. It's the same one that I showed in the previous slide, where we have a large number of sections representing walls of a variety of shapes. We have a large number of column sections as well, and beam sections, and a total of 10 load combinations. So these load combinations are SLS and ULS load combinations. So for the purposes of the concrete design, we're going to be focusing on the ULS, at least the concrete section design. When we get into foundation design, we'll also look at some of the serviceability load combinations as well. And that's where we introduce the multi-story designer workflow in S Concrete that basically allows us to import elements that we choose from an ETABS model. So we're assuming that that model that we just referred to came from ETABS. We've ran the analysis, we have all the forces and so on, and we're importing that data and choosing what we want to bring in, specifying some initial reinforcement on a section type basis, and then getting some results from some preliminary design checks. So we specify our reinforcements, get those results from the preliminary design checks, refine that design check, and we can even perform more detailed full S Concrete code checks as well if we want to. We can then generate all of the S Concrete input files, which is normally a very tedious workflow if we have to do it for a large number of sections that don't come from an S-frame analysis. However, this will actually facilitate that workflow for you, and then we can run it in the batch mode and generate result reports as well. You can see a few examples on the screen here. We can further refine our design groups, make changes, and go through an iterative design process until we're happy and generate a detailed code check output for our final documentation, including all the engineering design information that we need with clause references and code violations reported for us. So let's take a look at that workflow now. So here I have the S Concrete interface open. This is a standalone interface that allows us to design and detail reinforced concrete sections one at a time. However, we want to go a little bit beyond that. So what I'm going to do is I'm going to go to the Run menu and launch the S Concrete Multi-Story Designer. And here we can see that we have this screen that appears that allows us to specify where the data that we want to import from ETABS is located. So I've noticed here that I've got this MDB file, Microsoft Access Database file, and there's the format that you'll export from ETABS. We have some documentation on that. That contains all the information related to the geometry of the structure, the loads on the elements, and the size of the sections obviously as well, and where they're located. If you're not familiar with Access databases, you can see an example of the file here. If I look here, it has a number of different tables, and essentially just a database of spreadsheets, more or less. And so it contains information that you can actually manipulate in this environment as well, related to the element forces, the pier labels, and things like that. We can choose which information we'd like to bring in from that ETABS database. So we can bring in columns, beams, piers, spandrels, braces, whatever exists in our model. And for piers, we can also configure the shape of piers that's being imported as well. It will automatically detect based off the geometry that's been brought in, but we can override that if we need to. So you can see for this example, I've got a mixture of rectangular and C-shaped piers being brought in. we can provide additional filters on the actual individual sections that are being brought in, as well as which load combinations are being brought in. So for the case of as concrete, it's only dealing with factored loads. It's assuming all the loads are factored, so it may not be necessary for me to bring in these SLS load combinations, and so I can uncheck those and just keep the ULS instead. And finally, there may be situations where we want to group our sections in an efficient fashion to represent the best design methodology. By default, as Concrete's multi-layer designer is going to use the section label or the peer label to group like sections together. That means that any element that has the same section in the ETABS model will be part of the same design group by default. However, there may be situations, if I use an example of a column, where we have a number of columns of the same size, but perhaps the external columns will be reinforced differently than the interior columns. In that case here, we may actually want to use the ETABS grouping to differentiate those from the multi-story designer perspective. And here we can see that we can import those based off of their groupings in ETABS and import those groups as design groups instead. So I'm going to click the next button here, and we're going to read in the MDB file data and proceed with the preliminary design setup. So I'm now brought to the second screen in this workflow, and essentially what we're doing here is we're specifying some preliminary design information to help us represent the sections and their reinforcement. We also have the ability to control the design code. So for this example, I'll choose the ACI 2019 code, and we can choose the bar type or define our own custom bar types. And here we have tabs representing each one of our sections. And this allows us to initialize the information related to the reinforcement based off the cross sections being imported from ETABS. So we can specify the strength of our steel, for example. We can specify the percentage of vertical steel area that we have. So I'm just going to manipulate this default here. I'll say 1.1% for my row vertical steel, and the minimum vertical bar diameter can also be controlled along with the tie bar diameter. I'm just going to change this minimum vertical bar diameter to number 10 size. For the beams, I'll do something similar. So we have the ability to control the primary stirrup and sidebars. I'm going to change the primary bar size minimum to number 8. And for the sidebar, that's going to be number 5. And you'll notice here we also have top and bottom steel percent areas, or row, what I'm going to set to 0.75 for each one of these. And for the walls, I'm going to make just a few adjustments here. So we have obviously the ability to control the vertical and the horizontal steel. I'm going to change the vertical steel row from 0.2 to 0.3%, and the horizontal steel row here, I'm going to change it to 0.25%. Once I'm satisfied with all this, I can just apply all these design standards to the relevant sections, and the multi-story designer has now generated these sections based off those design standards I just specified. I'll click OK, and we can see here we have tabs for our walls, our beams, and our columns. And if I look at this list here, we see a list of all the different wall sections in the model. So the section names here are actually derived from the ETABS pier name, the pier length and the thickness, and the concrete material grade as well. So as you can see here, all of that represented in this label. And these parameters control which members go into specific design groups, essentially SCO files, and are checked based off of the properties in ETABS. Now we can also see here, we have in square brackets the word all. This just indicates that basically anywhere where this wall section is located, or this pier label is located, anywhere on any floor, we're going to consolidate all those locations and take the worst case loads from each one of those for design checks. There may be situations where we don't want that, in which case we can actually include story-specific groups as well. So I can say I only want to grab stories 11 through 14 to be designed together, and then the stories above that will be designed as a separate group. Or maybe each story is its own group as well. You can go into a lot of granularity. We can sort this information here because we noticed that it's actually giving us a DCRC and a DCRT ratio. And these stand for demand capacity ratios for compression and for tension. So basically we're performing a high level design check for the axial performance of the sections using the compression and tension capacities and comparing that to the applied loads. And we get a ratio, basically I'm using about 59% of the compression capacity for this particular wall, and it doesn't appear to have any tension on it. If I right click on this, I can click on sort, and I can actually sort based off of a number of different criteria. So here I can see I want to sort on the tension utilization. And I'll notice here that I actually have this particular wall that I've just highlighted has a utilization in compression of 0.67, but in tension of 1.23. So I'm about 23% over the capacity of this wall for tension. And what I can do is I can modify the parameters here for these design standards that I originally set up on either an individual section group basis or design group basis, or I can select multiple design groups and say, let's just bump up the vertical steel for all of these sections that I've selected. Or if I want to be more precise, I can actually left click on this design group and I can click on the wall form. And the wall form is going to open up a miniature S-concrete. And you can see it's got all the controls that we need to refine this section. I can see my utilization ratios again. I can see my zone reinforcement data. And for this example, I know that I have utilization over 1. So it may be worth my time to increase the zone reinforcement that I have. Perhaps I use a larger bar size. So right now I have 4 bars along the length of my zones and 3 along the thickness, and a number 5 bars in the vertical direction. So let me just bump that up first of all, go with a number 6 bar. And I can see that I'm getting a pretty good utilization with just that one change. However, I can continue on with additional changes, maybe because I want to get below 1, this threshold here. Maybe I increase the number of vertical bars along the thickness here to 4. When I make that change, I'm at the 0.93 ratio. And if I want to get even a little bit further into this passing status, I can bump up the length as well. So you can see here that the rendering will update accordingly. Now these demand capacity ratios are all based off of the axial code checks that are being performed. Again, it's looking at compression and tension. But if I want to run a full-fledged code check in S-concrete, using this form here, I just click on the Run Code Check button. It's going to ask me to keep these changes to apply them to my multi-story designer workflow. And now I'm getting a utilization report that's running the full S-concrete report, code check rather. So it's not only considering the axial and compression checks, axial compression and tension checks, but also the axial load versus moment interaction, shear checks as well. And you can see with this type of check being performed, my utilization is actually exceeding the capacity that's being given here. So maybe I need to make further changes, maybe a larger bar size and a few more bars. And this allows us to really quickly iterate on these sections en masse rather than one section at a time. So if I run this code check again, you can see that we're getting an acceptable utilization. I may be a little bit more bars than I need there, but the advantage here is that it's very easy for me to make these changes on the fly. And I can even open up this section in the standalone S-concrete by just clicking on this button, if I prefer that interface. So now when I go back, I see the new utilizations for this wall. And I can go look at another example here. Let's just look at a column. And I'm going to right click on the column here and I'm going to sort based off of the utilization ratios. And I can see I also have a column that's failing the code check. If I just click on the column form again, I can see that section and I can make additional modifications to it if I wanted to. So let's just look at our utilization ratios. Here we have our 1.67 in tension utilization. So I'm going to try increasing the number of bars again. And it may take some iterations as we've seen in the past, but we'll get to a point where we can get a satisfactory design and then proceed with our workflow. So I'm going to click the apply button here, and that utilization now shows up again. You may notice here that in some cases, the utilization ratios from this high-level code check will not necessarily match what we get when we run the more detailed code check. And that's to be expected again when we get the influence of the interaction between axial load and moment through the full code check. These are just meant to give you some high-level results, but when we run the batch code check in just a minute here, we'll be able to get more detailed results. And we can always continue iterating. So I'm going to click next here to proceed to the next step. And this is where we're actually going to generate all the SCO files that represent our different design groups. So here I've got a number of different section sizes for columns, beams, and walls, and the load combinations that I'm going to incorporate into those SCO files. And we just click the Create S-concrete Files button here to generate these files. At this stage, I could go ahead and run S-concrete in batch mode. So I can click on Run S-concrete Batch. And S-concrete is going to run a batch code check on all these sections, considering the full code check capabilities of S-concrete. So not just the high-level axial load code checks, for example, but also the interaction between axial load and moment, the shear checks, torsion, and more. And after the batch code check has been performed, we can look at the results. So here I can look at the code check results in a tabular format. Here I get a nice report in a tabular format again that I can export to an Excel file for additional post-processing. And this is showing me wall, beam, and column data that indicates basically the performance of all the sections along with additional parameters related to that section. So the total length of material, the thickness, the material being used, the reinforcement. And if I just scroll over to the right here, you can see some quantities. I can also see a list of messages. So this isn't just performing strength checks to let me know that my axial load and moment utilization exceeds a certain amount, it's also performing additional detailing checks. So it's looking at bar spacing, it's looking at stirrup spacing, and other information related to the actual detailing of these sections. I can create additional reports here. If I click on the Create Report button, I can export this information to a PDF file, or perhaps I want to create a schedule-like report with this option here, which I've already gone ahead and done just to show you an example for my columns. So this is basically documenting all the column design information, and it's broken down into story groups. So in order to do this, I had to generate design groups for each story, which is not hard to do. And now I can see the name of the section at each story, the utilizations, the reinforcement, and materials being used. So it gives me a really good understanding and a graphical representation of the performance of this structure, essentially, throughout the height of the structure. And it's very clear to me where I might have some issues and where my sections are doing okay. And finally, we can generate the detailed S-Concrete engineering design reports by just running the batch utility here. And I can browse to the folder of interest. I actually already have it dialed up, and generate a report or select the options that I want to include in my report. So it may be a scenario where I want to exclude loads, for example, because I have hundreds or thousands of different load cases that are just going to kind of take up valuable real estate in my report that I don't necessarily need to include for all 100 or 1,000 different sections. So we can toggle on and off whatever we need and click the Create Report button, and I actually have one open here for us. Let's just scroll to the top. And we can see here, if we scroll down, we get a list of the table of contents, basically showing us all the different cross sections in the section, in the structure. It's showing us the status of each, and the utilizations, and the page it's located on. And this is all hyperlinked. So if I want to look at a failing section here, I can just click on the name. It's going to bring me to that section. I'll just zoom in a little bit, showing me the utilization. So in this scenario here, I know that I have an issue with my N versus M results for a governing load combination number 193. In this case here, it appears that my factored moments are higher than my capacity, and I can scroll down and find additional details that might be of interest to me and the clause reference related to that violation. So it gives us a lot of useful information, and we can always go back and forth in this workflow to revise our sections again to come up with a design that's satisfactory to us. Now, throughout the multi-story designer workflow that we just went through, we were obviously performing design checks on reinforced concrete sections, and that's using the S-Concrete design engine. And for section design, it's powerful if we have it integrated with our existing workflow that we just showed you, but it can also be used as a standalone application to quickly and easily come up with design checks and optimization for reinforced concrete beam, column, wall, and slab band sections. It supports a number of different international design codes, including the latest ACI 318.19. We get instantaneous code utilization results out of it when using the interface itself directly. We can generate interaction diagrams and also comprehensive engineering design reports, just like we saw generated through that batch processing utility. So let's see how we can quickly jump into S-Concrete standalone instance and see this reinforced concrete column section then, designing according to some existing loads. We can see that we've got some utilizations described at the top of the screen, indicating an overall unacceptable status, but for shear and torsion, I'm doing okay. And for axial load and moment, I have some issues. And it's very easy for us to modify the section, either by just left-clicking on the hotkeys that represent the bar sizes and bar counts, and you can see that will reflect in the utilization reports. And I can also make changes to the geometry. So if I wanted to make this section deeper, for example, I left-click and drag, and it makes that section deeper, and that gives me two advantages. Obviously, I get more capacity, but I also have my row value decreasing as well, which is going to help with the detailing requirements that I need to meet. And you can see here with a few modifications, I'm now able to make this work, and I can go to the results report and see a summary of all the resulting information related to my design, including the utilizations, the governing load combinations, and all the parameters that went up to calculating this information. We also get into continuous concrete beam design, and this is an area that you'll see a lot of similarities between what we have in S-Concrete's section design and the continuous beam design, which is great for simple or continuous beam analysis, design, and reinforcement layout. So we support a number of different cross sections, and we can define different types of loads as well to represent the shear, the moment, torsion on the sections or on these beams. It's also got an integrated structural analysis, a finite element analysis, so it looks at both the SLS and ULS conditions and limit states, So a variety of different support conditions can be represented, cantilever, pinned, columns or walls sections above or below our beams. We can look at deflection based off of code-based effective inertia with considerations for cracking and creep, and design forces at faces of the supports and code-based moment redistribution. We also get member design and reinforcement layouts and reports. So we get complete member design and code checks along the span of the beam, accounting for reinforcement layouts and splicing, moments, shear, torsion envelopes. And the reports that are generated look very similar to S concrete with the same level of detail and include the code details for the controlling loads for each span on the beam as well. And we get into a variety of different design codes as well. We have the latest ACI codes, latest CSA codes. We also support the ACI 440 code for GFRP design, amongst others. Let us now turn our attention to foundation design. Now that we've designed the reinforced concrete sections in our structure, we want to design the footings underneath the structure. And for this, we can use S Foundation, which has the ability to design both deep and shallow foundations, and we can import our superstructure model from a variety of applications. For this example, we'll continue on with the same structure that we had before in ETABS. It can perform both structural and geotechnical checks. It also has an automated design capability and an integrated Python scripting window, which you'll be able to take a look at in just a second. So I'm going to jump into the software right now, and I have a blank model that's opened, but what I want to do is I just want to re-import that superstructure model from the ETABS model database, the MDB file here. So I'm going to go to the File menu, Import, ETABS, and it's already pointing to the MDB file that I had imported before for S Concrete. So I'll click the Next button. I can choose which components of the structure I'd like to bring into this S Foundation model, and exclude or include particular information that may or may not be relevant to my foundation design. I can click the import button. And now that the process is done, I can close this. And my ETABS model has been imported into S Foundation. You'll also notice that it's imported all the load combinations, which contain all the reaction loads at the support locations. So in this particular model, we have a number of different columns, and we want to design them, the foundations underneath these columns in different groups. So we have our end columns on the longitudinal ends at each end. We have our end columns on the, I would say, wider end, these two here, and the opposites on the other side, and all of the others in between for our spread footings. And we'll have a mat foundation underneath the core. And we can choose which load combinations are being run for geotechnical serviceability limit state analysis, and which are run for ultimate limit state analysis. And I can also configure the building code that's being, or the design code that's being used, and which design checks are being performed. So I'm going to start adding foundations to the structure, and I'm going to change to the plan view. And here from the plan view, we can see all the elements at the base of our structure. We've got a number of different column sections. As you can see here, we've got 2 columns on each side on the end, which are going to be doing a lot of the heavy lifting for this structure when it's being applied with wind loads and so on. We're going to have those designed as a separate group. So let me start with that using the spread footing tool or isolated footing tool. I can select the pad that I'm going to be using and the pedestal that I want to use, and simply just place that into position. Now it's worth noting that these pads that I'm drawing in are intentionally undersized, and we'll go through actually designing them in just a few minutes. But let's go and continue on with the next set of isolated footings that we're going to be using. And this is going to be called ISO B. We're going to give it a different pedestal size to match the size of the column. And the intention behind each one of these having their own pad and their own pedestal is that they can each be designed as a separate design group. So the end columns, for example, will have their own footings that have a different design group, and the forces on those columns specifically will be used to govern the design choices made for those columns. And so we won't over-design sections or columns that have foundations that are lightly loaded compared to their counterparts. I'm going to finish off with this ISO C, the 2 end columns on each of the wide angles here, or wide sides. And now my spread footings are in position. The next step is to define our mat foundation, and again I also have a mat foundation that is already ready to go. Now I specified this in the pad input tool, and here we can see the dimensions of the pad, the reinforcement and so on that's being used, and I can look at that pad in 3D and the reinforcement and so on that is being utilized. And now I have all my foundations in place. If I just switch to the view of my 3D structure, Here I can see I'm just looking at the elements that were connected to the substructure, the foundation. And since we have all the loads on this structure already, we can go ahead and start running a code check and analysis. Now for the sake of this demonstration and the limited time, I'm just going to focus here on the spread footings around the edges of the structure. So I can go ahead and run this analysis in code check. I'll click Run, Analyze and Code Check using the ACI 19 design code. And after the code checks have been completed, here we're getting utilization ratios for in this case here, the worst case result, which is pedestal structural axial force versus moment. And you can see here that we have some very high utilizations, which is to be expected. We haven't really put any thought into these design variables yet. We're just giving S Foundation something to work with. But what we can do is we can actually use a number of design wizards built into the software that will take this information, for example, the utilization ratios, which we can see here on the right-hand side, which seem to be, for the most part, quite high. And again, that's to be expected at this stage. And it can iterate on different design variables to come up with a solution for us for each one of our design groups. So it's using all the analysis results that are calculated. As we can see here, we have things like bearing pressures on our foundations. We have, as well as a number of other finite element analysis results. Let's take that information and let's run one of the Python scripts that actually ties together a number of different design wizards, algorithms, to iterate out to a solution that might work for us. So this is the Python script that's available to accomplish this task. And we can see here that it's actually going through and basically incrementing different design variables depending on the status or the portion of the script that it's working through. So it starts by designing our pads to meet soil bearing demands by incrementing the width and depth of the pad. Then we'll look into designing the pedestals by changing the rebar, the size of the pedestal as well, and then getting into the design of the pad for looking at things like punching shear and the depths of the pad, one-way shear and flexure, so the actual reinforcements as well. So let's go ahead and run this. And we can see from this design process, it's actually left us a script output of everything that's been accomplished during this design wizard. So if we just scroll to the top, we can see there was a number of different iterations performed to size the pad, the different pads, all three different types, to soil bearing requirements. If we scroll down a little further, we can see that there is some design changes made to the pedestals. Continuing on, we can also see that there's changes made to the depth of the pad for punching shear requirements. And in each instance, you'll notice we have pad 1, pad 2, pad 3, indicating the usage of the isolated footing A, B, and C that we defined. And if we scroll all the way down to the bottom here, is indicating to us basically the original thickness is 16 inches, which was a very preliminary, not even a guess, it was just kind of like a starting point. And then our new thickness, which is substantially more than 16 inches. And you can see it does vary a little bit between the three different pads. And continuing on, we run punching shear checks, or one-way shear checks, and we notice here that what worked for punching shear wasn't sufficient enough for one-way shear, so we've had to further increase those pad thicknesses. And then finally, for flexure, we're making modifications to our reinforcements as well, and we can see here the size of bars that we're using in our pad by the end of these iterations. So once we're done with all these changes, we can review them. We can look at any one of these pads, and perhaps we need to make additional changes. Like we can see here, some of the pads are quite close together. Maybe that's warranting a combined footing rather than separate isolated footings. And once we're totally satisfied with everything, we can go ahead and produce a report. So we can export a PDF report or an Excel report. And get the documentation required to basically pass this on to the next person that needs to consume this information. We can also see more detailed results under the design outputs, so we can look at things like not only quantities for our pad, for our rebar, for our concrete, whatever components that it is that we need, but we can see details of our actual design checks that have been performed as well. So if I want to look into the flexure checks, I can look at those and I can see exactly how S Foundation has come up with those for the different foundations, including the calculation of the capacities, the demands, and so on. Now hopefully you've been able to see throughout this presentation that the concrete design at Altair is very powerful, but doesn't necessarily require a long learning process to become proficient with it. It's also very good at minimizing any disruptions you might have to your workflow. It's a lot harder to totally replace an analysis program than it is to replace design solutions that work alongside those analysis solutions. And it's very easy to come up with optimizations for your design using these methods that we talked about and produce detailed engineering reports to document everything for you.